Welcome back to Chemistry B1B, covering Chapter 10.3, Phase Transitions, and more specifically going to be talking about vaporization and condensation. Now, this is showing what you need to know. You need to know the names of the different transitions, and these things are paired up. So, freezing is the opposite of melting. Condensation is the opposite of vaporization. Sublimation is the opposite process of deposition. Okay, now let's see, you need to remember exothermic. Exothermic is where energy is a product. Endothermic energy is a reactant. So for example, you could say H2O liquid plus energy produces H2O gas. Okay, and exothermic and endothermic are referring to the enthalpy, and I'm reminding you, Q is the symbol we used for heat, and we talked about a heat change at constant pressure. That was the change in enthalpy. And Q is a small letter, that's a path function. The heat of a process depends upon how you do it, but if you do it at a constant pressure, that's a state function, that's a capital letter, and that's where it doesn't matter how you do the process. It just matters the final state and the initial state. So you're going to be describing the energy changes associated with phase changes with melting, freezing, vaporization, etc. Explain how the intermolecular forces affect the enthalpy. Well, we said everything increases with intermolecular forces except vapor pressure. So stronger intermolecular forces, greater the enthalpy for a phase change. Describe at a molecular level what happens. So you talk about how the particles change, how their kinetic energy changes, how they separate or come together. You're going to define melting point and boiling point. And this last one is a big one. Given relative melting points, boiling points, vapor pressures, describe how the intermolecular forces compare and vice versa. 58, this is talk about vaporization and condensation. Now we're going to be doing this experiment. This will be our first experiment. Imagine you inject a liquid into this bulb. Now initially its pressure is the same as the outside pressure. You've got the outside pressure pushing on this open tube. So the mercury levels are the same because the pressure inside is equal to the pressure outside. As that liquid starts to vaporize, you've got more particles in the gas phase, and the pressure builds up, and that's this change in the height of mercury, and that's going to be the vapor pressure. Now vaporization and condensation, they're the reverse. Vaporization would be the liquid turning into a gas, and this thing can come to an equilibrium. Now what equilibrium means, the rate of vaporization is the same as the rate of condensation. When you're talking about a rate, you're talking about a speed. You're talking about a change with respect to time. And at equilibrium, liquid molecules are evaporating just as fast as they're condensing. Strong intermolecular forces are going to reduce vaporization. It's stronger the particles are held together, the less can make it into the gas phase. And weak intermolecular forces are going to allow molecules to escape and enter the vapor phase. Which of the following substances would have the highest boiling point at 1 atmosphere of pressure? Now, we said that all of our properties except one increase with intermolecular forces. So to answer this question, you've got to compare the intermolecular forces. Insert a table, and we're going to compare water, ethanol, And ether is another term for diethyl ether. And we're going to compare hydrogen bonding, dipole-dipole, and London dispersion forces. Now, looks like diethyl ether is the largest molecule, so I'm thinking it's going to have the largest. The ethanol is larger than the water molecule, and the water molecule is the smallest. Okay. And let's see, hydrogen bonding. You've got hydrogen attached to oxygen, and you've got two lone pairs on the oxygen. Those hydrogens on the water can hydrogen bond. So each water molecule can have 4 hydrogen bonds. For ethanol, you've got the two lone pairs on the oxygen. You've got the hydrogen attached to the oxygen, so you can get 3 hydrogen bonds. For diethyl ether, you don't have any hydrogens attached to that oxygen, so you've got 0 hydrogen bonds. Now, dipole-dipole, because you've got, and let's see, I want to go back to drawing. Okay. The oxygen's more electronegative. It's going to be a partial negative charge on that end, partial positive charge on this end. It's kind of small, so that charge separation is kind of concentrated over this small molecule. Ethanol is a bigger molecule. The charge is going to be spread out. The 2-carbon chain is nonpolar. This OH group will make the molecule polar, but I'm thinking it's not as polar as water. So I'm thinking largest, L-A-R-G-E-S-T. The diethyl ether, all these molecules have oxygen. You've got a couple of lone pairs. The bond angle is approximately the same, about 107. But with the diethyl ether, you've got these 2 nonpolar groups. I'm thinking, you can spread the charge out more, so I'm thinking this is going to be the smallest. And ethanol will be in the middle. So in the intermolecular forces, water is going to be the big winner. Ethanol is in second, ether is third. And we've said that boiling point tracks intermolecular forces, and the normal boiling point of water is 100 C. Ethanol, I believe it's 78. And diethyl ether is, 35. Now, body temperature is 37, so you could imagine pouring a puddle of ether in your hands and it would start boiling. And if you took a deep whiff of that, you'd pass out. We said water was the big winner for boiling point. For vapor phase, or vapor pressure. And let's see. Okay, I'm trying to draw here. All right, here we go. You've got a sealed up container, and this is going to be water. It looks like I left a little leak in there, so we'll close that up. Here's water, here's ether. Genius. And your ether attractions are pretty weak, so I'm trying to draw short arrows of attraction. Your water molecules, much stronger forces of attraction between them. So not many waters are going to get into the gas phase. You're going to get a lot more ethers because it's easier. They don't have as strong a bond to overcome to go into the gas phase. So ether of these 3 molecules at any given temperature Ether is going to have the highest vapor pressure, and water is going to have the smallest vapor pressure. Now let's see, let's just go back to our picture, and I compared water and ether. Imagine a piece of iron. I've got a bar of iron here, and very strong forces of attraction. The vapor pressure of iron is going to be incredibly small compared to water, compared to ether, because of the very strong forces of attraction. Iron, I believe you have to get it over 1,000 degrees Celsius for it to melt, and a much higher temperature for it to vaporize, to boil. So iron has very strong forces of attraction, very low vapor pressure. You don't smell iron on a hot day. Okay, you don't smell water either, but you sure will smell ether. All right. Now let's move on. And now these two curves, these are Boltzmann distribution. Ludwig Boltzmann came up with how to calculate these curves. But what it's showing is the number of molecules, and we're comparing a low temperature and a high temperature. And this is showing kinetic energy. So if you integrated these curves, the area under the curves would be the same. That represents the number of molecules. But the high temperature, you've got more molecules with more energy. So this dotted line represents the energy needed to escape the liquid. And you've got more molecules at high temperature that can escape. So as temperature goes up, the vapor pressure is going to go up. And you've seen this if you've washed your car on a hot day, the pavement doesn't stay wet very long. The water all evaporates. On a cold day, the water stays a whole lot longer because of that difference in vapor pressure. Okay. Boiling point. When the vapor pressure of a liquid increases enough to equal the atmospheric pressure, the liquid reaches its boiling point. Imagine you've got a liquid, and let's leave this liquid open to the atmosphere. So you've got the pressure of the atmosphere against it, and this is going to be at one temperature, and here's a higher temperature. And since it's the same container, I guess I need to leave that lip on it. Okay. Imagine that you had some molecules that come together. Now before I was using this as a molecule. Now it's a little bubble. And this bubble is going to have a certain pressure pushing on the liquid, but the atmosphere is pushing a whole lot harder. So this bubble will collapse. If it formed at a temperature lower than boiling, that bubble could collapse. Okay. Over here, this temperature is going to be equal to the normal boiling point. At the normal boiling point, this pressure, this bubble is pushing just as hard as the atmosphere is pushing. The force per unit area, that's what pressure is just as hard. And the density of a gas, you've got a whole lot less particles per volume. Density of the gas is going to be a whole lot less than the density of a liquid. So this bubble is going to float. And that's what you see in boiling. You see bubbles form and come up and break the surface. And so that's what boiling is. Now, the temperature of boiling is going to depend upon the external pressure. So when I say normal boiling point, that's when the surrounding pressure is 1 atmosphere. And what is standard boiling point? Okay. For a number of years, the people that come up with standards, the standard pressure is 1 bar. And I was about to write atmosphere. I'll go ahead and write an atmosphere is 1 bar. And Remember our old atmosphere, 760 millimeters of mercury? That is 1.01 bar. So they've lowered the standard pressure just a little bit. Okay. So, so the boiling point of water, the standard boiling point is going to be a little bit lower, not much, than the normal boiling point. Matter of fact, standard boiling point, and I left out the B, for water is 99.61, and the normal boiling point is 99.97. Sorry, it's not 100. I guess when more careful measurements were made, they decided, normal boiling point 99.97, not 100. Okay, now this asks the question, what happens to the boiling point in a place like Denver where the external pressure is less, and compare that to Siberia where sometimes the external pressure is higher. And this is showing how the vapor pressure changes with temperature, and this dotted line is the normal boiling point. That is 760 millimeters of mercury, or 1 atmosphere. And here's your diethyl ether with the very weak forces of attraction, and that temperature, hard to see, but that's about 35. Here is your water, and we said that was approximately 100. So as you're going this way, you've got larger intermolecular forces. Okay, and when we compare vapor pressure, we're saying at a constant temperature. So that's not a very vertical line, but as you know, like pick a temperature, and this curve right here, it looks like N octane. That has stronger forces of attraction than water, and that has stronger forces of attraction than ether. So ether is going to have a higher vapor pressure than water, than octane, and that's this curve over on the far right is mercury. Very low vapor pressure due to the strong forces of attraction. On the previous slide, it asked, what's the boiling point in Denver? Now, Denver has a lower external pressure, so you're going to be lower down on that curve, so you'll have a lower boiling point. I believe the boiling point of water in Denver is around 95 Celsius, so some foods are going to take longer to cook. And at a higher pressure, you're going to have a higher boiling point, and this is how a pressure cooker works. It seals, and you've got a higher pressure, so you can go to a higher temperature and cook faster.